jets and their afterglows and environments. So that's Andrew is going to kindly give us that talk.
Okay, thanks very much, Brian, and thanks for inviting me. It's a pleasure to talk about some really interesting work that's been done in numerical simulations of relativistic jets, which are obviously of relevance. So I'm going to talk about jets both in the case of GRBs, but also now GWs. So let me start by just setting the scene by showing you what we can do in terms of resolving jet propagation through a cloud or a surrounding medium. And basically, if there's an engine near a black hole or a hypermassive neutron star at the center of either a star or an ejecta cloud of the neutron star merger, what happens is really interesting. You get a relativistic jet, this core, that creates a cocoon around it by shocking the material in front of it, which gets pushed into a hot, magnetized, relativistic ball of gas that's being pushed through the cloud or star, which bounds a relativistic jet at its center.
So that cloud is the stuff that was created as the neutron star.
Yeah, so it's the cloud of ejected material before the engine turned on. So that's this material, and it gets shocked. And by the way, its temperature is very high, so if there are nuclei here, they get photodisintegrated. And we're calculating that now. And we actually find that a lot of this material can be destroyed along the axis. And that might be interesting for the blue component. Okay, after this jet breaks out of the cloud, what happens then is really interesting. And this is the afterglow phase, and this will take a second. But basically, we assume the engine is down here, and then you're in the ISM. So there's some low density surrounding material with a density of 10 to the minus 3 protons per cc in this case. And what's happened is all the energy that was injected by the jet has now been swept up into a relativistic shell, which we're going to focus in on right now. And this stretch shows you how hard a problem this is to do. So all of the energy is in this really thin structure that's traveling at nearly the speed of light through the ISM. And it's shocking the ISM. And behind the shock, there are accelerated relativistic electrons and magnetic fields which radiate synchrotron emission. And so what happens, this is the initial opening angle of this jet. And here is a model for when it was supposed to spread sideways, which it doesn't do, we found with these simulations. But it does eventually start to spread sideways a little bit. So if you're off axis, now you're starting to see radiation from this material. So that's lower Lorentz factor, and it's starting to spread sideways. Here's another model for when, theoretical model for when this was supposed to spread sideways, and it didn't. But eventually it does. It just does it 4 times later than had been predicted, and we can explain why that's true. So over time, this thing is sweeping up the ISM, then it's starting to expand sideways. Its asymptotic solution will be the set-off solution at late times. So it starts off at Blanford-McKee, but now it's transitioning to the set-off solution. So now this is becoming a non-relativistic shock that's kind of peanut-shaped, as you'll see in a second, and then that'll spread through the ISM, and it'll start to beam its radiation in all directions. So at late times, what we'll see is that even if you were off axis, you could see, completely off axis, you'd see light. So here's this peanut phase. And now, that's the jet and the counterjet. Then they're both going to slow down, become spherical, and they're going to collide along the symmetry axis here, which may have some observational possibilities at late times. I'm not trying to wait the whole time, but basically you can imagine what happens. This thing is an attractor. The set-off solution is an attractor, so it has to at late times become spherical, non-relativistic blast wave, and that's what's happening now. This is that collision that I was talking about.
So Andrew, just to make sure, so this is for long GRBs where you have a star that is collimates because it's going through the star and it collimates the jet. So you mentioned this also happens for the kind of neutron, so you just are a cloud, but how have you looked into that in detail? Yes,
I'm going to show you that. So this is agnostic about whether it's long or short. This is just a relativistic blast wave in the ISM. Whether it was launched from a short GRB or a long GRB doesn't matter. Yeah.
ISM, but one, density.
Yeah, the density is the only thing, and we use a range of density. We use 1 proton per cc, 10 to the minus 3, and 10 to the minus 5 to kind of cover the expected densities. Yeah.
And do you expect the jet to be launched only after a black hole forms or not?
Yeah, so that's a really good question. Is there a delay? So I don't know, and I think the best way to think about this is to turn it around and see if from the observations whether we constrain when the jet formed relative to when the merger took place. That's a really important issue. Yeah.
Is it also agnostic to the density profile?
No, this is a constant density medium as we'd expect in a neutron star merger, that at large scales, you're kind of out in the ISM. If you're in a wind medium, there's a different dynamics, but that's well understood, and we do both any power law. Okay, yeah?
Stratified medium?
Yeah, as long as there's not a characteristic length scale associated with the density structure, there's just a power law, then these, everything is self-similar in some sense.
And magnetic fields?
Okay, so this is hydro. Yeah, that's what I was thinking. On these scales, when you're this large, even if the engine was highly magnetized, the magnetic field out here is no longer dynamically important. But what is important is the magnetic field that's generated by plasma instabilities and probably turbulence as the shock accelerates electrons and generates magnetic field, and that's important for the radiation, which I'll show you in a second. But it's not dynamically important at this stage. Okay, so what's good then is we can take that jet simulation and rotate it, and then we can put a plane for an observer at an arbitrary viewing angle, and then we can solve the equations of radiative transfer through that time evolving thing. So we save all the time dumps of that simulation, and then we solve this transfer equation, sometimes just from synchrotron emission, but also with synchrotron self-absorption for the low frequency radio. Okay, so that's challenging, but it's doable. This is a relativistic thing. You have to have very high time resolution, but that's what we do. Okay, and so this is what we published a while ago. All the 3 panels on the top are for an on-axis observer, and this goes from the low frequency radio at 1 gigahertz all the way up to the X-ray. And this shows what would happen if you were off-axis. So here, you're near the edge of the jet. Here, a little bit further, and here you're about twice the opening angle of the jet. And what you see is nothing at first, right? Because all the radiation is relativistically beamed away from you, and it takes a while for that thing to slow down enough that the radiation beaming cone opens up and you start to see photons. So there's some time scale associated with that. And what we did is we put this on the internet, so we made it publicly available at this Afterglow library site. There are model parameters involved, but these are kind of well constrained, pretty much. The distance to the burst, the explosion energy, and the density, surrounding density. What really matters is their ratio. But what's interesting now is in addition to the jet opening angle, we can also constrain the observer angle. So we can create light curves for an arbitrary observer angle and an arbitrary opening angle of the jet. And then there's some microphysical parameters that involve the magnetic field that's parameterized as an epsilon b. And then we can try to fit these things. And Jeff Ryan did this as one of his first projects. And what's really cool is you can actually find data-driven evidence that the gamma ray bursts are observed off-axis in general. Let me show it. This is the Swift data for this particular GRB. It's a long GRB in this case. But doing all the fits, because the simulation's scaled, you can generate millions of light curves, theoretical light curves, and you can fit them with the Markov-Chen Monte Carlo procedure in order to get distribution functions for all of the model parameters. And what we're showing here is that the opening angle of the jet, which is about 0.05 radians, but here's the really cool thing. This is the observer angle over the total angle. So we're seeing this thing off axis. So that's got to be.
You're off axis, but you're still within.
Still within the cane. We saw the GRB. Yeah,
right. Just to be
yeah. So we'll get to orphan ones soon. But this is one where you did see. So this is the fraction. So we're at 0.7 of the opening angle of the jet. So you're like near the edge. Yeah. Okay. So that's found in these things. So in general, we find in all GRBs that very few of them are observed on axis. Almost all of them are viewed off axis.
Slightly off axis.
Well, if you saw the GRB, again, you had to be within the cone of the jet,
right. But
you're not seeing that. You're seeing the edge, right, which matters. And it's in the data. Okay, so this is interesting. So I just wanted to say, it surprised me when I went back and looked in the literature. The very first thing we did with this procedure is we made off-axis light curves for low-energy gamma ray bursts. And originally, I was thinking short gamma ray bursts, short hard gamma ray bursts, but for some reason, we called them low energy, which now is kind of a good thing, I guess. But the point was that data can be used to model fits to observational data, will benefit the study of neutron star mergers using different channels, such as gravitational wave observations with LIGO Virgo. So that was our idea in 2011. And then we put these online. And so here they are. This is X-ray, optical, radio and low frequency radio. This is the one that we did synchrotron self-absorption for. And what you're seeing is the solid line is on axis, then 0.2 radians, which is the opening angle of this jet, and then the other ones are off axis completely. So what you see is you don't see anything until about 10 days, right? And then you see something rising up and then fading, right? And so if you were way off axis, like at the equator, you wouldn't see anything for a month or something like that. So in the future, if there are other gravitational wave sources that are beamed completely away from us, these are the light curves we'd expect. And in fact, just to advertise this, I don't know if this will work, but these things are online. So you can go here, and this is these are the broadband and low energy off-axis light curves. And so that you can choose the energy, the circumference density, the frequency. So let's look at X-ray. And then you can choose the observer angle. So if we were observing at, let's say, 0.4, and you just submit it, and you'll see the light curve, and you can also download the data if you're interested. In this case, that feature at very late times is the counter jet. The jet that was moving in the opposite direction. Its radiation is now being towards you. Okay, now how do I get back? This was a mistake, maybe. Let's see. Let's see if this works. Nope. Sorry about this. Window. Okay. Yeah. Okay. Good. So here we are. Okay. So these are off-axis, on-axis, and slightly off-axis, and completely orphaned afterglow light curves. Okay. So here's the cool thing. In this paper by Troya et al., which Brad showed earlier, you can actually use that to constrain the viewing angle, the opening angle and the viewing angle of the jet. And this is what you get. So this is in the X-ray. If it had been on axis, it would have been like a normal X-ray afterglow of a GRB. But since it's off axis, you see nothing. And indeed, nothing was seen until about 9 days or something like that. And this is the afterglow library. These are light curves for what you would see in the X-ray. And this is what you'd see in the radio, right? And so those light curves, and this is I-band, what you'd see. And what they inferred here is that the opening angle of the jet was 15 degrees, very reasonable, and the viewing angle was 28 degrees. If it had been different, as you saw from the earlier ones, we would have seen X-rays earlier if we'd been closer to on-axis. If not, if we were been more off-axis, we'd have seen things later. So the time when you see these, and by the way, these upper limits are very important because they constrain the fact that you couldn't have seen X-rays earlier.
But there must be a lot of other parameters that you had to also adjust.
Yeah, there are. Yeah, but those are pretty well understood from. Yeah. Okay. So now the most recent things. Now I'm going to talk about are, I think, a really kind of revolution, I think, in numerical computational astrophysics. It's a code written by Paul Duffel, which is Lagrangian in the radial direction. It's a moving mesh. And you imagine, we're talking about stellar mass compact objects. So those have scales of 10 kilometers, 10 to the 6 centimeters. And what our job is to compute radiation that's produced on scales of 10 to the 13, 10 to the 17, 10 to the 18 for the late afterglow phase. So we're talking about many orders of magnitude, 12 orders of magnitude or more in length scale. It's very hard to do. What we did before, what I showed you earlier, was to use adaptive mesh refinement, so we kind of always changing the resolution dynamically in a very complicated way. This is much more elegant. So basically, the zones are moving with the fluid as it expands from scales now of a kilometer all the way to scales of 10 to the 18 centimeters. So we can do both the propagation through the ejecta cloud, as it breaks out of the surface of the ejecta cloud, as it becomes optically thin and forms a photosphere and forms photospheric emission, then as it plows through the ISM and produces late afterglow, orphan afterglow emission if you're off axis. All of that self-consistently in one simulation from the very center of the cloud all the way to the afterglow phase. And this is a Lagrangian code called JET, which is very powerful for these types of things. So let me show you a difference. This is so it's Lagrangian, so it looks like nothing is happening, but the whole thing is expanding. So you have to get used to thinking that way. So it's not, this thing is blowing up by orders of magnitude in radius, but what happens is if you're in the kind of co-moving frame, it's like cosmology in co-moving coordinates or something, what you see is the density on the left and the Lorentz factor on the right. And now it's broken out of the cloud. Now it's shedding a blast wave, which is opening up into the ISM. And now it's expanding many orders of magnitude. All of the energy now is in this little thin shell. And so what's great is now we can, and there's the cloud that was blown up down there. But now we don't need that anymore because this is causally disconnected. So we can excise that inner part. and now keep on going. So we're going now many, many orders of magnitude. This is 300 seconds, and we're going to go up to a year or more. All of the energy forms a very thin relativistic shell, very hard to resolve, but since all the zones are moving with the fluid, all of the zones now are in that little tiny shell. There's Kelvin-Helmholtz instability on the edge, and now you can see the Lorentz factor is down to 70. It started out higher, but now it's declining, and now all of this information can be used to calculate the emission that you'd see, again, from any observer angle, either on axis or slightly off axis, which we think is the case for this particular thing. Okay, and then there's some Rayleigh-Taylor instabilities, there's some interesting dynamics as well. But now look at this, it's at a year. And so it's on the scale of 3 × 10⁸ centimeters from something that started at 3 × 6 centimeters, so 12 orders of magnitude.
Andrew, is that,
yes.
If you go back to that slide for a second,
yeah.
Is that your inner boundary to your calculation? And what do you
yes,
for boundary condition there?
So this is outflow at this point, but at this stage, everything is moving supersonically away, so it's no longer in causal contact with this inner boundary condition.
Got it.
Okay, so this is the story. So this, so from 1 second to almost a year, we get this full dynamics, and so we can use that to calculate radiation. Okay, so for this meeting of interest, this is the first application of this. Paul Duffel ran these simulations, and the idea here is we took a prediction for what the neutron star cloud was. We're not burying the cloud in order to try to fit the data. We just found out about the data on Monday. So this is from 2015, and this was a numerical relativity simulation by Hodo Kozaka et al. Of what the cloud should be like. And in fact, what was interesting here is the cloud in their simulations was about 850 kilometers in radius, but it wasn't round, it was flat because it was blown off of a rotating system. And what we found is that even if we put a wide jet, so basically we don't know how jets are formed in gamma ray bursts or in general. So what we did is we modeled the engine as either a wide jet or a narrow jet. And what we found is that if the cloud is flattened, a thing that would be kind of a broad explosion and a round cloud is actually kind of quasi-focused into a jet that's kind of, an opening angle of, let's say, 20-something degrees.
So you say the cloud is a certain size, but then you're assuming the engine turns on a certain time after the merger, right? So
yeah, so very quickly in this case.
So like half a second or
something? No, even less. So yeah, so this was like 80 milliseconds.
80 milliseconds.
Yeah. So, okay, but anyway, so that's the thing that we can vary. That's one of the things that we can vary is when to turn on the jet. So in this case, that's what we chose.
Is your cloud static in this case?
No, it's expanding. Okay. Yeah. So that cloud is expanding with 0.2c, and it's like a Hubble flow. So it's 0 at the center, and it's expanding outwards. So this is exactly what they found in those numerical relativity simulations. Okay, but now we know how the jet breaks out, and the point of the study here was really just to focus on how the jet is focused. And that's what we found. And some really interesting things. If you look at the dependence of the terminal Lorentz factor and opening angle of the jet on the total energy of the explosion, what we found is for low energy explosions, they're easily focused by the cloud. But if you go to higher energy explosions, they just blast their way through the cloud and they don't get focused. Similarly, this is the relativistic energy fraction. Low energy explosions are kind of just trans-relativistic, but high energy explosions are almost totally relativistic. And the Lorentz factor then goes up to 1,000 for these very relativistic explosions. Okay, and then also, this is the comparison between the oblate and the spherical cloud. So the oblate cloud does a good job at focusing low energy explosions to opening angles of about 0.1 radians or 0.15 radians. Whereas if the cloud were spherical, it would have more trouble focusing it. So so we can learn about the geometry of the ejecta cloud is the point. Okay, this is another case where we find that the cloud, independent of what the engine is doing, whether it's a narrow jet at the base or whether it's wider, it's all focused by the cloud to this opening angle of 0.15. If, however, the engine was wider, let's say some sort of wind off an accretion disk, then it's harder to focus. So that basically what you put in is what you get out. You put in an engine of 0.8 and you get an engine of, well, 0.4. So it's only focused a little bit.
So for this event, people suggested 15 degrees, right?
Yes. Right. So that would be down here.
No, sorry, but it's
No,
an
no.
assumption of measure.
For the 15 degrees, you can fit the same data with
With wide ones, yeah.
With overflow.
Yeah, yeah, okay, so sorry, the other thing I should point out is that as this shock wave breaks out of the surface of the star, it's a lot like a shock wave breaking out of the surface of a star. So you have hot, relativistic material, and so you can get shock breakout emission, which can explain a soft gamma ray burst. And we know that already from low luminosity GRBs. So the same thing can happen in an ejecta cloud. Basically, the shock accelerates at the surface of the cloud, becomes relativistic, and the thermal emission is radiated as soon as it produces a photosphere. So photospheric emission can explain. So it doesn't have to be a very narrow jet. Okay, so what are we doing now? So most recently, this is the cloud. Again, it's the same cloud that was published already from the emerging neutron star numerical relativity simulations. And here we were exploring 3D is extremely expensive to do because we're injecting the engine at 3 kilometers, and this is 850 kilometers, but even so, we were able to do it in 3D. And what we find is that it's qualitatively similar to, actually almost perfectly the same as in 2D. So we just wanted to make sure. We can't do the huge simulations in 3D, obviously. Even in 2D, it's challenging. So we just wanted to confirm that there wasn't any big difference between 3D and 2D. So this is proof of that. And now, so this is work of Zhao Yiji, who's here. So now, this is a really cool picture. It takes a little second to explain. Here's the ejecta cloud, and here is the jet that's about to break out of the surface of the ejecta cloud. Okay, this is after 3 milliseconds. It's broken out, and this is on scales of 10 to the 9 centimeters, let's say. Okay, but now everything still is optically thick, so no photons are escaping yet. But what we can do here is then at 33 milliseconds, compute where the photosphere is. So here's the photosphere in purple, and you're starting to see that the energy in the jet, this is the density, is starting to break out through the photosphere. So that's after 30 milliseconds. Later, after it's expanded to 100 seconds, so 3 times 10 to the 12 centimeters, you get this kind of cool butterfly shape. And that shows where the photosphere is. So what we can do now is solve, again, the equations of radiative transfer for an observer at an arbitrary angle and find out what the photosphere is emitting. Because we know the temperature of the photosphere, we know its velocity, so we can just sum up all of the radiation with a Doppler factor to account for the fact that it's moving quickly. And then we can calculate a photospheric breakout. And then later, the photosphere, this is expanded even more now. This is 3 times 10 to the 14 centimeters. Now the photosphere is way down in the center, so it's this thing, a little bit bigger, but everything else is expanded. And so now we're seeing all the way down into that region. And at late times, everything is optically thin. So the photosphere is gone, and we're seeing a non-thermal emission from synchrotron, relativistic electrons. As this thing expands, all of the energy is in this really, really thin shell. And at late times, you'll see kind of what you saw in the earlier movie, which is just kind of a quasi-spherical blast wave that's now non-relativistic, colliding at the equator. But the point is, all of this information we can use to compute the light curve. So from the photospheric to the trans-relativistic phase to the Newtonian afterglow phase. And we can do this for all angles, all observers. Okay, so this is very preliminary, but just to give you a sense, this is Zhao work. What we can do here is we can compute as distribution of energy, because a lot of the early work on off and afterglows assumed that we had a top hat, just a constant energy blast wave, because that's an assumption you make on very large scales. But now we've propagated this jet, so from an engine, which we understand pretty well, it's got to have some luminosity and some rough opening angle, but then all of its sculpting as it comes through the cloud and travels through the ISM is calculated here. And so what we find is kind of a structured jet, which is pretty close to a top hat for these conditions. This was a low density, low mass cloud. It only had 10 to the minus 4 solar masses. And so what we find is that there's some structure here, but this is the kind of thing that we can use. This is the Lorentz factor at a bunch of different times, and we can use these also to calculate the light curves. The other interesting thing is at how much energy is in the cloud itself, how much is the ISM, and what's in the jet material, and see how that evolves as a function of time. It could be the case that the jet material itself and the cloud material itself is relativistically hot and it's accelerated electrons there. So there's emission from those components as well, which might be early emission. And then at late times, all of the energy is in the ISM, and that's when we have an external shock, and we calculate that emission that way. Okay, so here's a plot of the photosphere as a function of viewing angle. This is the density, here's the jet. And now if you're looking on axis, this is the photosphere you compute. But because of the Doppler factor, the opacity depends on your viewing angle. And so you see a different photosphere at different directions. This is 0.4 radians viewing angle, 0.8 radians viewing angle. And from this, Zhao Yi has computed the thermal emission that's Doppler boosted at a range of X-ray energy bands, both for an on-axis observer where it would be very bright indeed at that distance, it would be an incredibly bright X-ray source, but off-axis at about 0.4 radians, we get these types of light curves. Note that they're ones that have been tuned in the literature to get the 1.7 seconds. So you have to assume a very big cloud in order to get the photosphere really far away so that there's a delay between when the engine turns on and when you start to see the photons. We didn't do that. We used this photocosmic cloud. In that case, we see emission that lasts for a little bit less than a second, depending on frequency. Okay, and then this is for a different energy explosion, and so on. Okay, so the next thing I'd like to say is that when neutron stars merge, we know that they're shear past each other, and they generate a vorticity because of the Kelvin-Helmholtz instability when things shear past each other. And what we did is relativistic MHD simulations. This is the work of Jonathan Zrake, where he found that the kinetic energy of turbulence due to these shear instabilities should generate almost equipartition magnetic fields at the surface of the neutron star. Okay, and then later, and so this is kind of cool. This just shows how, if you take relativistic MHD and you stir a box with turbulence that's being driven on large scales by the Kelvin-Helmholtz instability, what you find is very quickly, this is very high resolution, you get a dynamo which generates a magnetic field. The red is magnetized material, so there's magnetic field fluctuating. But what we find if we put in the appropriate scale for neutron star merger is 10 to the 16 Gauss magnetic field. So what that means is, and that it starts on small scales, but it grows over time. And so this is the growth of magnetic energy. What we found is it happened on just a few eddy turnover times of the largest scale of the system. And so during the merger, just a second, please. Okay, so then what we did is we took that magnetic field strength and we put it into, this is work with Bruno Giacomatto, in full numerical relativity with neutron stars, but now for the magnetic, and this is MHD also, for the magnetic field, you put a subgrid model based on that turbulent dynamo, and we found that the magnetic field grows during the merger to enormous values. So we have, this is the energy in magnetic field, so we have 10 to the 51 ergs, and it's starting to converge, of magnetic field at our highest resolution, and the magnetic field strength is 10 to the 16 Gauss. So here's my point, the reason I'm mentioning this, is that if there's a neutron star left around after the merger, it should be highly magnetized, and that should be something that maybe you should be able to see later. So it's not just going to be some dim kind of shy neutron star. If it's there, it should be a magnetar. And so maybe that's something that will be seen later. Okay, thanks.
Time for maybe a few questions. Yep.
Fantastic simulation. Do you include the neutrino losses, and would they be important?
Yes, we do include the neutrino losses in those simulations, and they are important, because otherwise the gas just heats up too much.
That's what I was thinking, yeah.
Yeah. So no, but with the neutrino losses, it stays
so
kind
you
of
can
trimmed.
predict the neutrino burst.
Yeah, this is, yeah, absolutely, yeah. What we don't know is the neutrino sphere. So we'd have to compute that, but that can certainly be done. And
because the luminosity, that must be the highest.
It's 10 to the 53 ergs in neutrinos emitted over. So yeah, the luminosity is huge in neutrinos.
Then the other thing I was thinking about is with those magnetic fields, you have pair creation.
Oh, yeah. So we don't have that, but also from neutrino annihilation, you have pair creation. So that's also important. But from the magnetic fields, I don't know how you create pairs.
Can I sorry, I'm going to take the question. So in terms of this delay, we saw 1.7 seconds. And in terms of the time, I mean, if we start the engine, say, a reasonable time after the lifetime of the hypermassive neutron star, say 15 milliseconds.
Yeah.
And I know the jet head goes out slowly, so you think it's fully reasonable that delay could just be the jet head propagation time, or do we need something else?
No, and we need something else. The point is it gets out in a millisecond or something for this cloud.
For that cloud,
so,
yes.
So what you need is somehow to have a huge cloud. And if you do have a huge, massive cloud, then what you have is the photosphere can take a second to develop. Okay. So you can get the delay that way.
So huge meaning 10 times larger. So
even larger, I think. I think you need something like 10 to the 12, something enormous. So if somehow the neutron stars were blowing a wind earlier, or if somehow you're in a dense environment,
I mean, it has to be a really significant wind. I mean, it has to have an extent, but it has to have mass out there.
It has to have mass out there. But so if we just naively take what was published previously, before these discoveries, then that wasn't the case. And what we find is that if we turn on the engine 15 milliseconds after the merger, you'll see the photons 20 milliseconds after the merger. So
if I believe the simulations that before, then this would be saying that there might be evidence for a late starting jet.
Yes. But if you're willing to say somehow there's a huge cloud, which I don't understand, but maybe there is, then you could do it just with this photosphere.
So if the neutron stars are losing their guts out back as the merger is happening and they're ripping each other tidally, so you're generating this.
Yeah, that might help, but a lot of that material might be in the equator.
Right.
We care about this direction. So you need some sort of wind or something.
It would have to start really like many orbits before.
Right.
Okay. Why don't we? You set up, and then maybe one more question.
Yeah. So just follow up. What's the kinetic energy in that cloud?
The kinetic energy. Let's see. It's at 0.2 c. So 1 times 10 to the 10 squared, 10 to the 20 times 10 to the minus 4 is 10 to the 16 times 10 to the 33 is 10 to the 49.
Okay. Because the breakout time is essentially a function of the kinetic energy in the cloud. So if you had 10 to the 51 ergs, you could get 100 times longer breakout time scale.
Yes,
just very naively.
and that exactly. And so that might be the thing, is if you have a very energetic engine, and that would work with this photospheric emission, the shock breakout emission, then the engine is much more powerful. Only a tiny fraction is coming out in gamma rays, and you would have a big enough cloud to get the delay. So that would be a consistent story. Yes.
Okay. Let's thank Andrew one more time.
Oh.
We'll have hopefully some time for a general discussion, but